Stat E, 8.2.2, sampling distribution of sample means day 2. So in this example, the weights of RBA students, which includes the lower grades, are normally distributed with a mean of 140 pounds and a standard deviation of 20 pounds. Okay, so there's the information I first gave it to you. Now, what I've given you the information on is what our population looks like. So, if I took every single, Ryan, let's go. If I took every single student's weight, and I data collected every single student, and I calculated your weight, everybody's weight in the entire school, and I graphed them on a histogram or on a dot plot, that graph would be normal. Okay, it would follow a normal distribution, 68, 95, 99.7, everybody's weight. The mean, if I were to graph this, the mean would be 140 pounds. And if I added some standard deviations, I get 160, 180, 200. And if I went below, I get 120, 180. So basically, about 68% of students in this school, if this is not real information, because I don't know the weight of students. I don't have, I could estimate what the weights of the students are going to look like, doing it what we're doing here. But we're saying that we know this. So like 68% of students, the cutoffs, weigh between 120 and 160 pounds is what I'm saying here at RBA. Okay, it seems kind of reasonable. We've got a lot of younger kids and little peoples. And of course, about 95% of students weigh between 100 and 180 pounds. And most everybody, 99.7% of students weigh between 80 and 200 pounds. Now, I know, I was just putting these numbers up. These aren't real numbers. Maybe the mean is actually a little bit larger. Most likely the standard deviation might be a little bit smaller. The true population distribution in real life might actually be more skewed to the right. You might have students that are like maybe bunched up by the 90 to 110 pounds, the littlest people. And then the heaviest of students might be weighing way more. So it's probably not truly normal in the real life. But based on the context that I've given you, that's what we have. Question A, which is again, review from last unit. What is the probability that a randomly selected student weighs more than 125 pounds? Okay, so if I randomly select one student from the school, I number every student in the school 1 through 632, how many students there are. And then I put all their names in a hat, shake them up, or I use a random number generator, and I select one student. What's the probability that one student will weigh more than 125 pounds? Well, in this problem, they've told me that this distribution is approximately normal with a mean of 140. So they've told me the mean is 140 and the standard deviation is 20. We want to know the probability that is more than 125 pounds. So here's 125. and I want to find the area right there, because the area above that, which is again what we did in the last unit, represents the probability that a randomly selected student weighs more than 125 pounds. Now, we're getting a better than 50% chance, right? If the probability is more than 0.5, I know that for sure, because if the average student weighs 140 pounds, it seems more than likely than less likely that I would select a student that weighs 125 pounds. So the answer is somewhere greater than 0.5, of course, less than 1. So now how do I go about doing this problem? Well, nothing's changed. The area, the probability that a student weighs more than 125 pounds is a normal CDF problem. Once again, normal CDF, just like you did in the last unit. The lower boundary is 125. The upper boundary is 9999. It goes on forever. The mean is 140, and the standard deviation is 20. This is what you did over, and you did multiple times in the last unit. We've been doing this over and over and over. This here is normal model and not sampling distribution. The next follow-up question will be the sampling distribution question. Okay. Those of you who froze up or didn't know what to do and you were so confused on the last exam, you need to make sure you're knowing how to do this. So then I go to my calculator. I'll come back. Second vars 2, normal CDF. My lower boundary is 125, upper boundary 99. It's already in there from my previous class. Standard deviation 20. Paste, enter. And there's my answer. 0, I'm writing a pin here. 0.771. About a 77% chance. There's about a 77% chance that I pick a random student and they weigh at least 125 pounds. The probability is 0.771. You can remember, you can give me your answer. I prefer you just leaving the answer as 0.771. A lot of times in the context, people like to write it as a percentage and say 77%. You might want to say 77.1%, but that kind of sounds weird sometimes, so people will just say about 77%. All right, nothing new there. Nothing new there from this unit yet. Everything right here was from last unit that I just did. So now let's talk about the problem and make it this unit. We randomly select 10 students. Describe the sampling distribution of sample mean weights. Of RBA students. So now we're talking about the mean weights of size 10, all right, and that's important. So what is the sampling distribution going to look like for this sample of 10? So if I took the 10 students, if I randomly select 10 students and I calculate the average weight of those 10 students, what is that going to look like? Well, whenever you hear this question about sampling distribution, whenever you see this, describe the sampling distribution. Well, first, I guess we'll just sampling distribution. We're going to sin, okay? We're going to check the conditions. The first one, the sample is random. Yep, right? Says it right there. Random sample. Agree? 10, or so that's not a 10, it's a 1. 10% condition. And this one's a little bit, you're going to, 10% condition. 10 is less than 10% of all students. So we have to have less than 10%. Now remember, so that's a check. Now, as a reminder, when you do these two conditions here, we're really just checking for Is it okay that we can assume independence? You can't confirm independence. So it's an assumption that we make. Independence is an assumption that we make. And that looks really terrible in terms of how it's written. So in order to tell ourselves, is it safe to assume independence amongst each student? Is the weight of each student independent from the other? Because here's the reality, people. It's not. One person's weight is likely, there's two people here that are probably not independent. You know, you have a friend and your friend probably eats just like you, right? Or similar, right? You eat out, they eat out, you skip lunch, they skip lunch. You're on the softball team, they're on the softball team, soccer team, whatever it is, you probably have somebody whose weight is probably not truly independent. But in the context of assuming that if I randomly select these 10 individuals, is it okay to assume that these 10 individuals will be somewhat independent? And the answer is yes, as long as these first two conditions are met. And I'm not going to be a big stickler on you. If you don't talk about this independence part, that's fine. If all you do is get me what's in here, that's going to work. Okay? And there we go. So, and then the last condition is the normality check. Which, because we're talking about sample means, it's the nearly normal. All right, is this nearly normal? It's a nearly normal condition. If this was proportions, we check success failures. When it's means, we check nearly normal. Does anybody remember the magic number? The magic number for the sample size that always works for us? 30. The sample size is 30. Boom, I'm done. I could just say n is greater than 30. I'm good. Is n greater than 30? No. So it's 10. 10 is not greater than 30, but that's fine. So because the population is normal. So 30, so n equals 10 is okay. Because remember, what I told you that every time we take a larger sample size, as we increase the sample from 1 to 2 to 3 to 4, every single time we do that, the sampling distribution becomes more normal from what the population distribution was. But if the population distribution is already normal, then it's still normal, right? If you're already normal and I make you more normal, you're normal. I'm not really doing anything to you. But if you're slightly not normal, then I can make you more normal, and it just depends, the bigger, bigger, and bigger. So remember, n greater than or equal, n 30 is our magic number no matter what. So if n is not greater than 30, there's going to be some more information that I'm going to give you. Yesterday, what I did is I gave you the graph of the distribution of the population. And we looked at it and said, yeah, that looks already kind of normal. So we did n equals 5 was good enough. All right? So if n is normal, so we're good, approximately normal. The mean of the sampling distribution is equal to the mean of the population. So what will be the average weight of these 10 students? 140 pounds. Nothing changes there. If the average weight of a student is 140 pounds, then the average weight of 10 students will be 140 pounds. Make sense? That's what, like, clean cut. But what about the standard deviation of the sampling distribution of sample means? Now notice, but again, I use that little subscript, and you're going to see that within the Desmos today in terms of identifying that. Well, the standard deviation of the population was 20, but ours is not 20. It's 20 what? It's not 20. No. We got to do a little bit of math to it. You let Mal carry you? Someone want to jump in? Over square root of n, which is in this problem 10. Be careful there. Don't forget for the sampling distribution, don't forget to divide the standard deviation of the population by the square root of 10. There's less variability. The more people you get, the more closer you're going to get to the average amongst them, which is 6.32 pounds. So basically, as you're writing this, what we're doing here, from a conceptual understanding, what you have to say is like, as we take bigger sample, the average of the weights is going to vary less from the mean. Because the more people you keep plucking and sampling, the more likely that each one of those individuals was going to be closer to the average weight. One individual on their own. If you walk down the hall and you saw one student who was weighing 200, or let's say, who weighed 180 pounds, would you be shocked? Probably not. Okay, one heavy individual, maybe 200 pounds, you probably wouldn't be completely like, something's wrong with this school. If you walked down the hall and you found one student, but if you found 10 students and the average weight of those 10 students was 200 pounds, now you're going to say, wait a minute, something's up. Same thing on the other end. If you saw one student who weighed 100 pounds, probably like, okay, I mean, genetics and some, just maybe athlete, maybe whatever the reasons. One student. But if you saw 10 students and we sampled 10 students and their average weight was 100 pounds or less, we'd probably say, wait a minute, something's going wrong. Something's wrong. One person weighing 10 pounds, not that unusual. 10 people whose average weight is 100 pounds, something must be up. Maybe there's an eating disorder around the school, or maybe there's something that's a trend that's how much people are weighing. TikTok said something about weight. I don't know what it. But that's the kind of thing we do as statisticians. We look at these samples and we say, ooh, that's weird. Question C, which is the last one. What's the probability that the mean weight of 10 randomly selected RBA students is at least 125 pounds? Now, what I hope, and some of you were saying yesterday this, some of you were saying like, wait a minute, isn't this asking me the same question as I just answered in question A? And the answer is no. Question A was asking me about one student using the population. Now we're talking about the sampling distribution. And every sampling distribution is different, and it depends on the sample size, which is 10. But we just did that. So we're literally going to use our answer from B. We're going to use this information right here because we've already shown that it is true to do this problem. So I'm going to answer this problem, I make a quick sketch. The center is still 140. So my mean of the sampling distribution is 140. The standard deviation of sampling distribution is 6.32, or 20 divided by square root of 10. Some people just leave it like that, 20 over square root of 10, or I like to put it into decimal form. And 125 will be way over here, and I want to find what is the area for here. So for all intents and purposes, math-wise, it looks almost identical to the original question from last unit. The only thing that's different really is that we have a different standard deviation. Why do we have the standard deviation that's different? That's what we learned in our previous part. So the probability that the average weight is greater than 125 pounds is normal CDF, 125, comma, 9999, comma, 140, comma, and I'll write it a little bit different this time, 20 over the square root of 10, which again is the 6.32. You can write it as 20 over square root 10, or you can just write 6.32. I'm writing it at that purpose for notes so that you understand where I'm getting that number from. So when I do normal CDF to, the only thing I have to change is this is now, it's 20 divided by the square root of 10. Oh, again, if I wanted to replace that with 6.32, I could have also done that. But I'm just pointing out, the only difference between question A and question C is the standard deviation being now 20 over the square root of 10. And there's my answer, 0.991. So, in conclusion, for today's lesson, an example that you're going to be working from here on out. The probability that one student weight exceeded 125 pounds was about 77%. There's a 77% chance that I randomly selected one student who weighed more than 125 pounds. Whereas the probability that the average weight of 10 students exceeds 125 pounds is 0.99. It's very, very, very likely. So we're almost certain, it's not certainty, but 99% probability, there's a 99% chance that if I randomly selected 10 students that the average weight would be at least 125 pounds or more. And that's a lot about what we understand. That the concept is very simple, but it is, a lot of students have a very hard time understanding it because we're not talking about an individual, we're talking about the average of individuals. And the expected average stays the same, but the variability decreases by the square root of n.